Welcome to the lecture. Today we'll be talking about DC to AC converters. So DC to AC converters are commonly known as inverters. So what does it do? So it changes a DC input voltage to a symmetric AC output voltage, and if we want, we can control the output voltage magnitude and frequency. Practical inverters produce non-sinusoidal outputs with harmonics. So inverters are used in many fields. So here are some examples: variable speed AC motor drives, then in renewable energy sector and in transportation sector, and also you know about UPS. Types: we can categorize inverters in various ways. For example, single phase and three phase inverters. Then we have voltage source inverters where the input voltage is constant, and in current source inverters the input current is constant. And if we can control the input voltage, then the inverter can be called variable DC linked inverter. We have another type of inverter which is called resonant pulse inverter. So an LC resonant circuit is used so that the output voltage or current passes through the 0 point. We can use some performance parameters to evaluate the performance of the inverter. So output power, we multiply the output voltage and output current and the power factor. AC input power, we multiply the supply voltage and supply current. RMS ripple content of input current, we can get it from the subtraction of the RMS value and the average value of the current. Ripple factor of the input current, we compare the RMS current and the average current. Power efficiency of the inverter depends on switching losses, but we can control the switching losses by controlling the switching frequency. So here is the block diagram. On the input side we have DC, on the output we have AC. And in general, the inverter produces a square wave AC output. But we can make it sinusoidal, or at least try to make it sinusoidal as much as possible. This is an example of half bridge inverter. So here we have the DC supply, we have two filter capacitor on the input side, then we have the load. So 0 to A is our terminal. So we can have only the resistive load or the resistive plus inductive load, RL load. And on this side we have two switches, Q1 and Q2, and we have two diodes, D1 and D2, connected anti-parallel with the switches. So what we can do is that for 50% of the time we turn on Q1, and when Q1 is turned on, Q2 always has to remain off. So when Q1 is on, then the current flows from the supply through Q1 through the load and goes back to the source. So here the direction of the current flow is from right to left. Now when Q2 is turned on and Q1 is turned off, then what happens? Then current still comes from here. Okay, let me just change the color. The current comes from here and goes back there. So now the direction of the current flow is from left to right. So here we can see that when Q1 is on, then we get a voltage of Vs divided by 2, and when Q2 is on, then we get a voltage of minus Vs divided by 2. And if we are using only the resistive load, then theta is 0. We get current by dividing the voltage, that is Vs divided by 2 divided by R. So the formula for RMS output voltage, we can calculate the RMS value. So the output is Vs divided by 2, so we square it, so Vs square divided by 4, and we integrate it from 0 to 50% of the time, and then we multiply it by 2 and then average it by dividing by the time period. So we get an RMS output voltage Vs divided by 2, or 50% of the supply voltage. RMS value of the fundamental component is actually less than that, so we have 45% of the supply voltage, and we can also calculate the DC supply current. So if we use inductive loads, then what happens? So when, let's say, Q1 is on and the current flowing from right to left, then if we turn off Q1, at that moment what happens? There is some energy left inside this inductor, and when Q1 is turned off, so it still flows from here. So it actually flows through the diode D2, and when Q2 is on and then we turn it off, what happens? So when Q2 is on, then current flows from left to right, but when we turn off Q2, at that moment this excess energy that is inside this inductor tries to flow through this path, so it cannot go through Q2. So what happens? It goes like this, so it goes through D1. So you can further analyze it with this figure. Now we can look at an example. A single phase half bridge inverter has a resistive load of 2.5 ohm and DC input voltage of 48 volts. Find the fundamental components of the output voltage, output power, average and peak currents of each transistor, and average supply current. So this should be 45% of the supply voltage, and the output voltage is 50% of the supply voltage. And output power, we can divide the square of the voltage divided by the resistance, and we can get the current by dividing the voltage with resistance, so we get 10 amps, but each transistor only remains active for 50% of the time, so we only get 5 ampere on average for each transistor. And average supply current, we can divide the power with voltage. This is the circuit diagram of full bridge inverter. So we have our supply on the left side, then 2 filter capacitors on the supply side, then we have 4 switches, switch 1, switch 2, switch 3, and switch 4. So the operation would be that we have to turn on Q1 and Q2 together. So when Q1 and Q2 is turned on, then the current would flow like this. Back to the source. So we can see that our load terminal, output terminal, is here. So this is terminal A, this is terminal B. So we have the direction of the current like this. Now let's see what happens when we turn on Q3 and Q4. So when we turn on these 2 switches, Q3 and Q4, what happens is that the current goes like this. And now the direction of the current flow is like this. So we can see that for the 50% of the time, if we turn on Q1 and Q2, then the direction of the current flow is from left to right. And for the other half of the cycle, if we turn on Q3 and Q4, then the current flows from right to left. So this is the wave shape for highly inductive loads. So we can first inspect the switching states. So full bridge inverters can have 5 switching states. For example, if we look at state number 1, then here S1 and S2 are on. So if S1 and S2 are on, let's see what happens. So let's say S1 is on and S2 is on. So what happens is that the current flows like this. And this terminal A, is connected to the positive of the supply. So VA with respect to 0 is Vs divided by 2. And this terminal B, is connected to the negative of the supply. So VBO would be minus Vs divided by. So to measure the voltage between the terminals A and B, we can check VAB would be Vs divided by 2 minus Vs divided by 2, which gets us Vs. Okay. So from this table, so S1 and S2 are on, so we get Vs as our output voltage. So for the other states, you can just go to the circuit diagram and check the values of these two terminals. The RMS output voltage would be equal to the RMS supply voltage, and the fundamental component would be 90% of the supply voltage. Now we will look into three-phase bridge inverters. Three-phase bridge inverters can have two types of control signals: 180-degree conduction and 120-degree conduction. However, 180-degree conduction has better utilization of switches. Here is an example of how a three-phase voltage source inverter can be used in practice. So we can see there is a wind generator, and the output of wind generator is rectified using this rectifier. Then the rectified DC signal is fed into the input of voltage source inverter. This voltage source inverter produces AC signal which is appropriate for this grid. Here is the example circuit for 180-degree conduction. So we have supply voltage, and on the right we have 6 switches. We also have 6 diodes connected anti-parallel with the switches. Each transistor conducts for 180 degrees. 3 transistors remain on at any instant of time. There are in total 6 modes of operation in a cycle, and the duration of each mode is 60 degrees. And the transistors are numbered in the sequence of getting the transistors. So for example, the switches 1, 2, 3 can be on at the beginning, then the switches 2, 3, 4, and then 3, 4, 5, 4, 5, 6, and so on. If we look at this waveform, we can see that G1, G2, these are getting signals. So we can see that the switch 1 can start at the beginning at 0 degree. Then the second switch starts after 60 degrees. Then the third switch starts after 120 degrees, and so on. So if we look at the output voltages, line-to-line voltages, VAB, VBC, and VCA. So VAB would be maximum, and it would be for 120 degrees. Then VBC would be maximum positive, and it would be for the next 120 degrees, and VCA would be the next one. Okay, so from this switching table, we can see that this type of topology can have 8 states. So we can see that the state number 1, so we have VAB equal to VS, VBC equals to 0, and VCA which equal to minus VS. Switch state 7 and 8 produces 0 voltages. Okay, so we can inspect what happens in the first state where S1, S2 and S6 are on. Okay, so we can see in state 1, S1, S2 and S6 on. So that means this one is on, then S6 is on and S2 is on. That means this terminal A is positive, terminal B is negative, and terminal C is also negative. So VAB would be VA minus VB, which would give us VS divided by 2 minus VS divided by 2, because VB is negative. So it gives us VS, which we can verify here. Yes. Now for VC, VB minus VC, so VB is negative, minus VS divided by 2, minus VC is also negative, so minus VS divided by 2, which gives us 0. So we can see VBC 0. Then VCA, VC is negative, so minus VS divided by 2, then minus, then VA, so VA is positive, so which gives us minus VS. You can see minus VS. Now let's go back to the waveform. Okay. At the beginning, VAB is maximum. Then after 120 degrees, VBC becomes maximum, and then VCA. So what we can see here, that at the beginning, switch 6, switch 5 and switch 1 are turned on. So 6, 5 and 1. Now after 60 degree, what happens? This one, and this one becomes on. So switch 6, then switch 2 and switch 1. So we can see from this pattern, the next one should be 1, 2, 3. So 1, 2 and 3, which gives us this one. And for this one should be 2, 3 and 4. So 2, 3 and 4. So by correctly modulating the getting signals, we can get a proper output 3-phase voltage.